Hey everyone, in this video I'm going to be going over the mechanism for the reaction of an addition of some halogen across a double or maybe even a triple bond. So let's get into it. Let's say perhaps uh, we have the following reaction and we're trying to figure out how to make it go forward. Well, if we want to do a reaction like this where we have two halogens that are oriented anti to each other, so anti-addition, we are going to take our starting material, so some carbon chain with a double bond, and it can be as simple as adding, X2 being some halogen and then some solvent. So I'm going to choose, there we go, there we go. So this is what we're going to have, and where x2, so x2 can be several things. You can be Br2, maybe even a Cl2. What's iodine? Maybe iodine might be purple actually. Do I have a purple? Yes. So maybe we have iodine, and then I don't know, fluorine. I don't know what color fluorine is. Uh, so now you're supposed to suggest a mechanism to make this reaction go forward. So what might that look like? Well, let's go ahead and replace our X2 with one of our halogens. Let's use Br2. So Br like this. And so what we can expect to see, and if we threw all of these things into the same pot, we'd see the double bond going through one of the carbons and attacking one of the bromines. So the reason this can happen is because it's energetically more favorable for uh, for bromine to have a negative charge than it is for this double bond to be neutral, like it is right now. So we will create then our bromine, and now we have a plus charge right there, and don't forget that we still have this hanging out there. So uh, now what's going to happen is instead of what might be the kind of catch here is that there's a correct way to add our bromide ion, right? So we can see maybe we could add it this way and get the syn addition, but in truth what will happen is we'll see the anti-addition. And this just happens because of steric effects where we have an already kind of big bromine atom that gets attached to our carbon molecule, and then we have this bromide ion that can't really, you can't really push past that too easily. And so it's much easier just to go around this way, following the arrow, and attach on the opposite side, which gives us the anti-addition, which is what we were looking for, right? So some things to note about this reaction. It is sensitive to the solvent that you use. So let me kind of give it its own section. So solvents. It is picky to the solvent you use because if you use something that's protic or anything that has the possibility to interact with a bromonium ion or a bromide ion or even a double bond, you're looking for trouble. So we usually use inert solvents like we have CCl4. That's usually a pretty good solvent. You don't really see the chlorines wanting to pop off of a carbon, especially uh, you'll create a carbon, either anion or cation, which is usually whenever it's just one carbon, that's unfavorable. It's very hard to do. So maybe we'll even see something like methylene chloride. So that's what is that? That's CH2Cl2. Um, and then other possibilities, you can maybe even find an ether that would work. So I'm going to put that one in brackets because that one is still pretty sensitive. You'd want to find a good ether solvent that would satisfy the reaction. So let's take a look. What would happen if perhaps instead of following the list of solvents I've listed, what if we use something like water, right? So we have our basic kind of generic molecule, and for a solvent we use something like uh, let's use we said water. Well, we can see the same thing happening, right? So let me get rid of that too, and let's draw it a little bit nicer, right? So we're going to draw it like this. So the same first step would likely happen. We'd have our double bond going through a carbon, just maybe draw it like that, going through that carbon. And then the bond between the two bromines gets kicked off to one of them, and we've created our first intermediate. So we have our plus right here, and a Br right there, and we have a Br plus, and we have H2O. So great. It looks like, oops, I'm sorry, that should have been a Br minus. So it looks like we're in a good position right now, right? But really what's going to happen is this H2O isn't really just one H2O molecule. So if we're using it as a solvent, it's probably going to be a little bit in excess. So really this one H2O, isn't just there. We might have one that's right there. Maybe we have another one over here. There's another H2O. So this whole pot that we're running the reaction in has several different water molecules. And, just by inspection, just look that this one water molecule is so much closer to attacking this this carbon cation than this bromide ion is. So it's going to be more likely that we see a an oxygen giving a lone pair to this carbon cation way before we see this bromide ion making its way over there. It's just going to be too slow, and the water solvent is going to take its place. And so, I don't know. Let's just carry this through. So, what would we have? We have, there's our bromine attached, and now we have OH2 plus, and we still have a Br minus, and then, you have some water still somewhere. So, you know, uh, one of the bromines are going to come over. They're going to steal a hydrogen, and I should draw this better. I should draw that better so that it's a little bit more clear. There's another hydrogen, and let me correct this line by making it just a little bit more towards what I want. And so that bromide ion will come and take this H off of the water and satisfy the oxygen cation, or the oxygen positive charge. So then we've satisfied the reaction, and we have now an OH and a Br. So we've created, instead of a dibromo species, we've created some sort of an alcohol with some sort of halogen attached to it, which, if you remember from the previous slide, that wasn't the goal. We wanted to make a dibromo or some dihalogen uh, product, not an alcohol and some other halogen. So this isn't quite helpful for us. So that's why we don't use water. So uh, I'm going to show a little bit more now. Okay, I have it redrawn here, and I just want to touch on a few more points before I end this video. So It's important to note again that this is an anti-addition problem, or reaction rather, and if these were chiral centers, or if we just want to depict this a different way, we might draw it, you know, we might draw it with one coming out at us and the other one going back. You might see this notation for how it is drawn to just emphasize that these are being attached in an anti-addition manner. As far as regiochemistry goes, regiochemistry, well, there is none. And that should be pretty obvious because, whichever one we attach first or however we attach them, we're getting two bromines on either side. So it doesn't matter, or we have no concern for regiochemistry for this reaction. So you can also run this reaction with triple bonds. So, you know, uh, oops, that's a really bad line. The only problem that you can run into, and maybe it's obvious, is, well, first we can see that we'll get to maybe this part. Let's see, is that right? So that's 1, 2, 3, 4 carbons, and we should be like that. And we'll get one bromine attaching here, and maybe the other one attaches like that. Well, who's to say that the reaction stops right here? Why can't the reaction continue going, right? So you can see the reaction. It's possible that, I'm going to use yellow for caution, that it happens again. So we have another Br2, and then more of our solvent, whatever, and we get another anti-addition. So like this, and do our original ones in black. Oops, they should actually be anti. Like that. And so, this is a real possibility. So if you want to run this sort of reaction and you want our product to be this one, well, you're going to have to find some sort of restraints to add to your reaction. Maybe you cool it, or you find the right time that you can stop a reaction, or maybe you just let it go and you separate it by distillation, or I don't know, maybe you could do chromatography, or whatever it is that you're using to separate it. But this is just something to uh, just take into consideration if you plan to do this type of reaction with triple bonds.